Hi, I'm Mike Alperin, Manufacturing Industry Consultant at TIBCO. I'll introduce this demo and show how the results are visualized in Spotfire. Then Stephen Hillian, Senior Director of Data Science, will go through the TIBCO data science workflow that performs all the big data calculations. This is a manufacturing demo about digital twins for yield. It's about analyzing manufacturing equipment sensor and process data at very large scales to understand the causes of product defects. Digital twins are virtual representations of physical systems. The recent intense interest in them is fueled by the convergence of IoT, machine learning, and big data technology, all directed at the growing volumes of data available from sensors on process equipment. As the process complexity increases, these digital twins are becoming really key to efficient operations and high product yields. If we look at this diagram, on the top we see a manufacturing process flow that's composed of a sequence of process steps. At each process step, there may be sensor trace data from multiple equipment sensors. For example, pressure and temperature sensor readings will evolve throughout the course of a process step and can be visualized with sensor traces. There can be a large number of process steps in the flow. For example, the latest 3D flash memories are approaching 1,000 steps, and each step will have its own set of sensor traces. In addition to process steps, there are measurement steps in the flow where physical measurements are made on the product during production. Once the processing is complete, the product is tested. There will be a determination of whether the product fails or passes all tests. If you aggregate that pass-fail data up over a large number of parts, then you get a percent yield, which is the percentage of passing parts. But often it's not good enough to just look at the pass-fail data. You need some information about how the parts fail, their failure modes and patterns, in order to have the best chance of later determining why they fail. So you can decompose the total yield loss into components. There are many ways to do this. The components can be based on the bin group the failing test belonged to, spatial patterns of fails on wafers, the anomaly cluster failing parts belong to, or some combination of the preceding. So if we take this product test data and combine it with all of the process data, we can create a model for each yield loss component as a function of all the process parameters. That is the digital twin yield model. Remember, there can be hundreds of steps and millions of individual process parameters, so big data technology is going to be needed. These digital twin models can be used in different ways. They're a guide to improving the process. It would also be advisable to consider monitoring the important process variables. And finally, the model can provide feedback to dynamically adjust process inputs in flight for maximum yield. If the system is architected for high performance, it's possible to automate and run these digital twins continuously to capture new relationships in real time just as they start to emerge. So a new problem at a process step that is impacting product yield will reveal itself as soon as material with that problem is tested. On this page, we're doing the big data analysis, comparing the yield loss for one failure mode to the sensor readings for all of the processes. For this initial set of data, there's only a low level of yield loss and not much variability from lot to lot, which we see on the top trend chart. The heat map shows the digital twin results for the yield cluster. Each row shown represents one of the sensors in the process, and the columns represent a time series for that sensor. Cells are colored by variable importance. So the heat map shows which sensors and process times we should examine to understand what is driving the yield loss. So let's go ahead and mark some lots in one of the sensor rows. The actual traces for that sensor are now visible in the chart on the right. We've colored the anomalous versus the normal wafers, but we're not seeing much of a difference, probably because the variable importance is actually very low. So yeah, these might be the most important sensors, but we're not seeing a very strong effect. We can look at other sensors represented in the heat map, but there's nothing very interesting happening in this time frame. Now we go ahead and rerun the model for the most recent set of lots. When we do this, we're rerunning the TIBCO Data Science Big Data Digital Twin Yield Model and populating the heat map with the results. In the second part of this demo, we'll go into detail on what is happening in that workflow. Now we see a dramatic difference between lots and the yield loss trend. Some have a significant yield loss while others don't. Let's go ahead and mark some good lots and some bad lots, and this top sensor, which is showing a high variable importance for a number of process times. This allows us to drill into the actual sensor traces. We're seeing the good stuff has elevated readings in this portion of the recipe, while the bad material is flat there. So this is very significant. We're able to go directly from product yield loss to assess which are the most important sensor readings that correlate to those losses, and we can actually look at differences between good versus bad sensor traces. This may provide an important clue to understanding the cause of the yield loss. That's great, but how do we actually generate the heat map data, visualizing the most important results for millions of predictor variables in near real time? So now we'll look at what's going on in the TIBCO data science workflow that's generating the data visualized here.
Here in our TIBCO data science workspace, we've created an advanced analytics workflow that computes the variable importance metrics that Mike was just showing on his dashboard. In brief, it does this in three main steps. It does this first by reducing the length and complexity of the sensor time series data using the SACS encoder. This converts it into now thousands of input variables, down from hundreds of thousands of input variables. And we can now compute the correlations between the outcome of the manufacturing process and this wide data set of thousands of input variables. Then we can filter out those that are less significant, less tightly correlated with the outcome, and feed those into a random forest regression to compute the final importance metrics. Let me open up the workflow now and walk through the details. Okay, so here we see the input data with one time series per, here's the time series here on the right, and there's one time series per lot, wafer, and sensor. And you can see the time series is pretty long, in fact, about 1,000 points long. Now, with 100 sensors, in this case, that means that we have 100,000 variables that might influence the outcome, and for which we therefore would have to compute the importance. Now, we can't feed all of those into a standard regression model, at least not easily. So instead, we're going to do some variable reduction first. The method of SACS encoding reduces a long time series to a smaller number of aggregated values, sometimes expressed as a sequence of letters or a word, in this case expressed as in numerical form. Now, there are several options, computational options, that you have in the SACS encoder method, but just to keep it simple, in brief, what it does is to take, in this case, I've isolated just one time series. It takes a long time series of about 1,000 points and reduces that to a time series of just length 50 in this case, but as you see, without losing any of the critical information. Now, the output of the SACS encoder is expressed in this tall and narrow form of about 30 million rows and about 5,000 variables. So you have tall and narrow form expressed in these name value pairs, or these variable value pairs. And this pivoted form lets us handle what would otherwise be a very wide data set. It lets us use the pivoted form to handle the wide data set more easily. Now, we combine these variable value pairs with the outcome of the process, also expressed as a name value pair. And that then we can feed into the wide data variable selection operator, which simply computes the correlations between the input variables and the outcome. So here are the correlations, and we can put those into a histogram. And if we look at the histogram and look at those sort of clumped in the middle with the lower correlations, we see that the least interesting variables are those with correlations between about minus 0.14 and plus 0.17 or 0.18. So we can now filter out those with low correlations, join back to the original data set. Now with a smaller number of variables, we can then pivot this back into a standard table of variables as columns, and then feed this into our random forest regression to compute the variable importances. And here you see, as in Mike's dashboard, it seems like sensor 4 is the one that's really of most interest. Now, at each stage of this workflow, we are doing all of the computations, including the 3 main algorithms here, in Spark. We're pushing all of these algorithms down to be computed in Spark, running directly on the input data in Hadoop. And that means no data movement and essentially unlimited scalability. And even with millions of input variables, this flow runs in just a few minutes.
Thank you, Stephen. In this demo, we introduced the concept of product digital twins. They correlate product test results directly to time series data from large numbers of equipment sensors. This was previously a laborious, multi-step, time-consuming process that we have now completely automated. We showed how Spotfire enables business users to easily visualize and understand the results produced by a complex TIBCO data science workflow. That workflow rapidly processes large volumes of time series data for near real-time results.